but they do provide those data products. And then Tropomi, because it looks farther into the infrared side of the spectrum, also produces data products relevant for carbon monoxide and methane. And here's just a side-by-side comparison to see the new capabilities that Tropomi has on the left. So this is the same day data from both instruments. I wasn't able to visualize it in the same platform, so the color scales are not the same, obviously, but you can kind of see, with OMI, the larger pixel sizes, so a coarser spatial resolution, more gaps between the satellite passes. That's due to basically the degradation and capabilities of the instruments. It's been operating for 20 years now, versus the newer instrument Tropomi on the left, much higher spatial resolution, so you can see much finer details of the NO2 column, and a wider spatial coverage, so less gaps between the data. So in terms of the specific data products, just to briefly talk about them, ozone, I mentioned, is a very difficult thing to look at from space from an air quality perspective, because of the ozone layer. Of course, the ozone layer is very useful for blocking ultraviolet radiation, but if you're looking at from an air quality perspective, that thick layer of ozone higher in the atmosphere interferes with our ability to really detect the near surface ozone, which is more relevant for air quality. So while there are these ozone data products from satellites, they're typically not recommended for use for air quality, simply because so much of the signal is relevant more to the upper atmosphere, not necessarily the surface. Conversely, nitrogen dioxide tends to be concentrated much more near the surface, which is where most of the emissions happen. And so it's much more commonly used for air quality applications. There tends to be a better correlation between what the satellite's seeing in terms of the NO2 column and what surface monitors might see in terms of NO2 concentration. And again, both OMI and Tropomi provide those data products. I mentioned Tropomi is a European instrument, but due to an agreement between the European Space Agency and NASA, we are able to share the Tropomi data out using our web platforms as well. Formaldehyde is another interesting product. For air quality, it's basically typically used as a general proxy for all volatile organic compounds in the atmosphere. And in particular, if you look at the ratio, which is what's being done in the figure here, the ratio of the formaldehyde to the NO2 from a satellite data product, it's sort of similar to if you would look at the VOC to NOx ratio concentrations, which has implications in terms of ozone formation potential. So as I mentioned, while we can't really use satellite data products to look at ozone directly, we can infer indirectly some information about the potential ozone by looking at the formaldehyde and the NOx and making some assumptions and ratios there. Sulfur dioxide, another data product. Now, typically, the satellite capabilities are only such that we only see really big sources like volcanoes, like big coal and oil burning, or some smelter plants. Large smelting activities will sometimes show up, but like a backyard diesel generator or a highway with diesel vehicles going by with sulfur content in the fuel won't necessarily show up unless it's a really severe emissions. But in some cases, especially for volcanoes and things like that, it's useful to look at sulfur dioxide from satellites. And then I mentioned with Tropomi, looking further into the infrared, we can get information on the carbon monoxide and the methane. Carbon monoxide usually used as like a tracer and an indicator of biomass burning, so wildfire activities or agricultural burning, things like that. And then methane, a greenhouse gas indicating, could potentially be indicating some methane producing activities from natural gas activities. There's also distributed sources of methane, especially agricultural activities as well. So in addition to just looking at the concentrations in the atmosphere, we can also use models to infer what the emissions might be from specific sources. So I'm showing here using the satellite sulfur dioxide data. They've actually identified and quantified these various major sulfur dioxide emitting sources around the world. And you can see here, as I mentioned, it's really the big sources that are being detected: the volcanoes, smelters, major power plants, and then oil and gas production and refinement activities are the sources being indicated here. But this is the basic idea here, is that you can use the satellite data along with some assumptions and some modeling to infer emissions of these gases as well. So now talking a little bit more about integrating the air quality from satellites with surface data. And the kind of the fundamental concept here is that surface and satellite data can provide complementary information. So this is an example from Rwanda. On the left, there's a satellite-derived PM2.5 data product plotted over the area for a specific monthly average. And you can see with that, we get very good spatial coverage. We have most of the country covered in that data set versus the three small circles in the city of Kigali itself were the only ground-based data we had access to during that same time period from low-cost sensors deployed there. Conversely, on the right, with those low-cost sensors in Kigali, we were able to look at the temporal profile in the red on the right, and look at how PM2.5 varied throughout the day. And if you compared that to the blue rectangle, which is the times of day during which all the satellites which went into producing the figure on the left were passing overhead, you can see that this just so happens to be, for this particular area, happening at the times of the day with some of the lowest concentrations. So if we just look at the map on the left, we'd get a good idea of the spatial coverage, but we wouldn't really get an idea of the temporal variability and, the fact that this might be the low concentrations, lower than the average concentration for the whole day. Versus, the plot on the right, we get a lot of that temporal information, but it's for a very small subset of areas. So by putting these two information sources together, we can hopefully gain some more insights that we couldn't get with each data source individually. And there's a couple of different kind of broad strategies for doing something like this. The first is maybe looking at spatial patterns and spatial correlation. So looking at the measurements at a discrete set of locations over an area from ground-based monitoring and comparing that to a map derived from satellite data, something like aerosol optical depth. And just looking at the correlation between those two, and is there a good agreement or is there not good agreement? If there is good agreement, that's great. You're getting the same kind of story being told to you from the satellite data and from the ground data, so that's good corroboration. But there are, of course, many confounding factors that can lead to poor agreement. There's the fact that the satellites are only passing over at specific times of day. There's the fact that the satellite information might be blocked by cloud cover, and that clouds may be more or less prevalent over certain areas or at certain times of the year. There's different land use, which might affect, closer to the emission sources, the pollutants might be concentrated closer to the ground versus farther away. The pollutants might be higher up in the atmosphere. The satellite can't make that determination, so it might look at those two areas and say that they have the same pollution level versus a ground-based monitor would be able to tell the difference there. So there are many factors that might lead to those disagreements, and then investigating those factors might give you some insight into the air quality situation and why it is the way it is. Similarly, looking at temporal correlation. So here I've plotted, I think, this was for Kampala, the satellite aerosol optical depth and the ground-based PM2.5 from the U.S. Embassy monitor there, and the monthly averages. So broadly speaking, you can kind of see a similar trend where they're trending up and down together, but there's also a lot of nuance and areas where they don't trend together. For example, the ground-based monitor basically all the time showed higher concentrations in the morning than in the afternoon. Versus in the satellite data, these satellites were passing over in the morning and the afternoon, but it's not necessarily that the morning aerosol optical depth was always higher than the afternoon aerosol optical depth. It actually varied month to month. So again, some areas of broad agreement, but then some areas where there could be confounding factors that cause disagreement. So investigating those might lead you to some more insights into what's actually going on. Another example here, McFarlane et al. Looked at, on the left, comparing the 2019 to 2020 aerosol optical depth over Brazzaville and Kinshasa. And that red color in the figure on the left is indicating a decrease in aerosol optical depth as we went from 2019 to 2020. And that decrease is more pronounced closer to the urban area, likely the result of travel restrictions and activity restrictions due to the COVID-19 pandemic. Similarly corroborated with the ground-based data on the right, showing this decrease from 2019 to 2020 in overall concentrations, and especially that pronounced change in the afternoon peak, which again the satellite was passing over in the a pronounced change in the evening peak where the satellite was passing over in the afternoon, so it was seeing a less severe reduction there. Another example for gas, for carbon monoxide, looking at in the figures on the left, the top figure shows more rural areas and some villages in Malawi. The box plots are indicating the ground-based measurement data from low-cost sensors, and then the light blue line is indicating MOPIT, which is a satellite data product for carbon monoxide, and then the light yellow line is indicating MERA2, which is a reanalysis, basically a combination of model and satellite data, one of those level 4 data products I discussed earlier for carbon monoxide. So, and then the bottom is the same thing except in a more urban area. So you can see sort of very broad qualitative agreement in terms of all the data sets agree that there's higher concentrations during this biomass burning season, August to November, but there's quite a bit of quantitative disagreement. And again, there's many factors which could be influencing this. The monitors are at very specific locations, so they're measuring the concentrations at very specific locations, whereas the satellite data and then especially the model data is looking at averages over a wider area. So it might be, on average, the whole area might have a lower concentration, but at specific locations where the measurements are being made, the concentrations could be quite a bit higher. All right, so talking a little bit about satellite data for, using models as the connection between these two, between satellite and ground data. And I want to here sort of introduce one example model, which is the model that my office produces, which is the Goddard Earth Observing System Composition Forecast, or the GOCF model system. And what this basically does is it combines a global meteorological model system, which is being informed by satellite data in terms of the meteorology, with a chemistry module which tracks about 250 different chemicals and aerosols in the atmosphere. And this is being run every day to produce sort of a one-day simulation of the prior day, as well as a 5-day ahead forecast based on the forecasted meteorology for the next 5 days. And this is being run at on a 1/4 degree grid across the world, so that translates to roughly 25-kilometer spatial resolution at the ground level. And for the chemical species that are relevant for air quality, at least, the temporal resolution is basically hourly for this data set. So this is an example of a simulation model and a forecasting model which produces data relevant for air quality, and it's informed by satellite data to a degree. It's not necessarily taking into account like the aerosols or the aerosol optical depth or the column trace gas concentrations, but it is informed by satellite data to the extent that the meteorology of the model is being informed by satellite data. And in the version 2 of the model, which we hope to develop and release in this year, we will be making more of an effort to take into account things like the aerosol optical depth and the column trace gas concentrations in these estimates of air quality relevant parameters. So, how well is this model doing in general? I'm showing some figures here evaluating it over sites in Africa. And, broadly speaking, there's some agreement there. SO2 in particular is a place where this model is doing quite poorly. It's vastly overestimating SO2 here, so we don't recommend its use for SO2. But for the other relevant constituents like ozone, nitrogen dioxide, PM2.5, broadly it's capturing the trends. There are, of course, limitations here where, for example, with the PM2.5, there's only 9 at the time this analysis was done. There were only data from 9 ground-based monitors.